Good afternoon, everyone. So today's class we are going to start looking at how a DC motor operates. And before we go ahead, does anybody have any questions regarding the homework? It's quite a bit of a long homework, so hope you all have started early. If anybody needs extension, that's absolutely fine. Take till Sunday at noon. I have set the assignment to be published on Sunday 1 p.m. So try to submit before that. After that, I won't be able to accept any assignments because I can't delay the posting of solutions because some students will start preparing early for the midterm. So try to submit, not try to submit by Sunday 12 p.m. By noon, right? Okay, so today's class, we are gonna look at DC motor going forward. All that we need are these set of equations. From our mechanical model, we have this equation from our third lecture. And then from our electromagnetic theory lectures, we have these definitions. Let flux over closed surface is 0, go around the loop, integrate the H field. That needs to be equal to I conductor total and H itself. The relationship between V and H is some kind of constant. So in case of materials like air gap, this mu r is just 1. In case of material like silicon iron, this mu r can be as low as 4,000, as high as maybe sometimes even 20,000. If you can remove the carbon impurity to the maximum extent possible and inject silicon instead, you can get this mu r much, much higher. Right? And this mu r is not per se exactly a constant because depending on how deep into saturation you are, this mu r value changes. If yep.
Sorry, just when are you gonna stop teaching information for the midterm?
Oh, we are done. So
okay,
yeah, whatever was last week, that was the content for midterm. Right, whatever we are covering today is not part of midterm. We have done.
With mu r, the higher the number, the better that, I guess, conductor is. Is that accurate? Or
so if you had conductivity, it would be a better conductor. If it had higher mu r, it acts better as a ferromagnetic material.
Yeah.
So better conductor for flux in some sense. Right?
Yeah. Okay.
Yeah.
There may not homework before the midterm, like this.
No, they won't be homework. I am not that kind of. So any other questions? Right. So yeah, this mu r changes depending on where you are on the BH curve. Right. For except when we look at the case of magnets, we won't think of cases where mu r are varying. Right. Only in the case of magnet, we look at the complex curve and try to figure out which point in the BH curve are we operating. But otherwise, when we have when we're looking at iron or when we're looking at air gap is always going to be assumed 1, or at least for the magnetic fields we are working at, air gap is as good as free space. And for iron, we are always going to assume that it's not going into saturation. In reality, in motors, iron would be operated somewhat well into saturation in certain parts, like the teeth of the rotor and stuff like that. But for our consideration, we can just assume it's not saturated. Right? If that's the case, then we can just assume it's a constant. And then the final equation for the EMF is n d phi by dt. It's up to you whether you want to include the negative sign or not. But when I ask you to plot the EMF, you need to make sure that the phase angle between the voltage and the current, the EMF and the currents are correct. All right, so you'll have to figure out, or if I give an inductor and tell you which direction the flux is and how the flux is varying, you should be able to plot the polarity of the EMF on the diagram, right? So these are all set of one more, and the force is going to be equal to L times I cross B. So these are the set of equations that we are going to be using in this lecture, and going forward to whatever we learned in the first 3 weeks, 4 weeks, all of it can be ignored or if you at the end of the course just take away these 5 equations, right? Okay, so let's start with today's lecture. I have to do a little bit of juggling. I have multiple cameras here, so it will take a little of time for me to get a hang of it. So this is the structure we are going to be looking at, right? So we will see how this all plays out in the actual motor in a couple of minutes once we understand the basics. But what we have here is basically just a north pole and a south pole. And then we have a conductor in between. And we are going to see what the forces acting on these conductors are, right? So can somebody tell me what the first problem with this diagram is? Yep.
Shouldn't there have to be like flux lines outside of the magnet as well to make the the divergence zero?
Yep. So the diagram that I've drawn here is not how it would actually be in a motor, right? So this is how all textbooks would like to draw the motor magnets, but we already said there are no magnetic monopoles. So for every north, there should be a south. So when I draw this north, what I essentially mean, whenever we see this, that means this face, this side is north, then the back side would then obviously be south. There is no option. And when I say this pole is south, that means the face that is facing the conductor, which is what I'm interested in, is south, and the back side is north. And in a motor, what would happen is, I'll show it in the document camera a bit later. So we have two magnets inside. So one face is north, the other face is south. And then the flux lines flows through the shell itself. Okay? So this is an iron shell. So the flux lines will flow from one south to the other north through the back shell that we have. Right? So there are no monopoles. So whenever I draw this north pole, it just means that the space that is interacting with the conductor, it shows a characteristic of a north pole. The other one shows the characteristic of south pole. All right. So field lines leave the north and field lines terminate at the south for our, the convention we have. And within the motor's outer structure, these field lines will close back. Right. So this is how they would end up closing. Oh, sorry, going from north to south. Okay, so once I put this conductor inside, let's say I'm passing current through this conductor, going in this direction, coming out and completing this loop here. So I have some voltage source connected here with positive on this side, negative on this side. So this is the current that starts flowing. What is going to be the direction of the force on the conductor? Let's say the conductor on your right, my right. Your right, sorry. So the conductor near the south pole, what is going to be the direction of the force? Is it going to be upwards or downwards? Upwards, thank you. So our magnetic field is along this direction, going from north to south, right? So this is a B field. And our current is going in this direction, right? So this formula is I cross B. Turn your hand around, and the force is going to be perpendicularly upwards. Right? So this is the force that we have on the conductor on the right. So our force is going to be upwards. What is going to be the force on the conductor on the left? It's going to be upwards that way. That one also is going to be downwards on the conductor on the left.
Down.
Downward. Thank you. Okay, so because previously the current was coming out of the page, now the current is going into the page. So basically the current direction reversed, you can just put a negative sign for the previous case and the force would end up being downwards. So what we have created is effectively force on two conductors. And if there is some kind of mechanism that on which this conductor is pivoted, so this is what the pivot would look like, where we have a rotor structure, right? And we are looking at just one conductor turn, right? So there is a central pivot over which this thing can rotate. So once we have force, if there is something to which it's pivoted on, it's going to start to rotate, right? And so what is going to be the force? So we have some current I. Let's say the length of this conductor is L. So the length would mean this vertical. So the length would be the vertical length of the conductor, right? So the magnets are on this side and magnets are on this side. Current is going into the conductor and coming out of the conductor and coming out this way. And then there is magnetic field coming from this side. So the length is basically the axial length, all right? The way I've drawn it here, it's you're looking at it in this view. So once, so we have our force, and R is going to be the radius of this loop. So starting from this point, from the pivot to the end of the conductor. So from the center of this pivot, rotor pivot, to the end of the conductor, that's going to be a radius, rotor radius. So R times I times B. That is going to be the force experienced by the conductor. What is going to be the torque? Oh, sorry. L times I times B. Right? Length of the conductor times the current times the B. What is going to be the torque?
How far it is from the center of the shaft?
Yep, that length I've given as R. Okay, so that's the center of the shaft is the orange line that I've drawn going into the board. So perfect. So if that length is R, what is going to be the torque?
Oh, R times F.
RF, thank you. R times L times I times B. Is that the only torque acting on the loop? What else?
The other one.
The other one. So this is one torque acting on it. There is a torque on the other side acting on it as well. Right. So that is gonna. So we have torque on the left conductor is R L I B, which is going to be same as the torque on the right conductor. So the total torque is going to be 2 times R times L times I times B. And so this is our loop. This was our radius R. This was our length L. What is this term going to come out to? 2RL for this loop. The loop area. So 2R is just going to be the total area, total length, diameter. So this is just going to be our loop area. So pretty straightforward. Just the loop area times the current in the conductor times the magnetic field B. Right? So everybody clear so far? Right. So what we are going to next do is we are going to look at what happens. So because there is a torque now acting on this conductor, right? There is a torque pulling. So there is a torque pulling this conductor this way, this conductor downwards. So this conductor is going to start rotating in the anti-clockwise direction. So now the conductor, let's say, rotated by some angle, let's say 45 degrees. So what is going to be the force? Is the force going to be different from the previous case? So in the previous case, the force was L times I cross B. Is it going to be different this time? No. Is the current and the B field still perpendicular to one another? Anybody says no? It's still perpendicular, right? They are in the two different planes. The current is in this direction still. The B field is in this direction still. It is just the conductor moved up. That's it, right? So the angle between the I and the B did not change. They are still perpendicular. So this is still going to be I times B. There is going to be no sine theta, cos theta, none of those going on in that expression. What about the torque? Is the torque still the same? No, because when we look at the force here, so we have a force acting like this. You can resolve it into two components. In the previous case, there was a force. So this was a conductor. Our force was perfectly perpendicular to it. So all of the force was contributing to torque. So the formula for torque is not just R times F, it's R cross F. Right? Only the component of force is perpendicular to the loop is going to cause rotation. So whatever this force we have, that can be broken down into our component that is along the loop, and then the other component which is tangential to the loop or perpendicular to it. Right? Only the component of torque that's perpendicular is interesting to us. So let's say this loop angle is some theta. Right? What is torque going to be? L I B sin theta or cos theta? Don't try to solve for the geometry. Just think what will happen if theta is 0. If theta is 0, that was a previous case where all the force was creating torque. So that has to be a cos theta projection. So it's always a little bit tricky to figure out, thinking of geometry, taking this angle, taking this here. Don't need to complicate it all. If this collapses to 0 degree, then this torque has to be maximum value. The cos theta function is what gives you the torque characteristic. Right? Everybody clear so far? Okay. What is going to be the torque when the conductor goes to 90 degrees? Is there going to be a torque on the conductor?
0.
0. So in this case, all the force is going to be along this direction, right? There is going to be no torque on this because there is no torque along the perpendicular component of force is 0. Right? Perpendicular is 0. That means the torque is also 0 at this point. Right? Is the conductor still going to continue to rotate, or is it going to stop there? Stop. Okay. How many of you think it will stop? Just raise your hands. You have only two options. Half the class, whether you better raise for this or for the other option. How many of you think it's going to stop? All right. How many of you think it's going to continue? Why will it continue? Inertia. Same as with pendulum, right? So when we have a pendulum case, let's say we pull this pendulum all the way to this point. and release it. Here the velocity is 0, but the acceleration is maximum. So the pendulum will start. But at this point, the velocity is maximum, but the acceleration of the pendulum is 0. Right? This is exactly behaving like a pendulum now. Even though there is no force, that means there is no torque, there is no perpendicular force, there is no torque, there is no rotational acceleration. But rotational speed is still not 0. Previously, it was rotating at some speed. Even if you remove the force, right, it's going to continue to rotate at that speed. So it is going to continue to rotate. A torque is definitely 0, same as in case of a mass. You apply some force and you remove that force after the mass reaches some velocity. Right? Even if you remove the force, the acceleration goes to 0, but the velocity of the body still continues. So the system has some stored energy and the inertia is going to continue to rotate. Right? So it is going to go to a different direction. What will be the direction of force? So if you look at this, the conductor, the one that's marked as red, started off at the left, right? And now it has completed almost 135 degrees of a turn. So the conductor on the red, current is going like this. I'm not going into full screen because I don't have the multiple color pen option there. But yeah, so the current is going into this and coming out of this conductor. What is going to be the direction of the force in this case? Let's say for the conductor on your left, upwards. Perfect. Because this is the same as the case we had in the first one, right? Conductor on the left, conductor on the right had current coming out of the page and the force was upwards. Here the same thing. The B field direction did not change because the magnets don't move around. So the B field is still like this. The current is still outwards. It's just that previously the red conductor, this conductor was on the right. Now it has come to the left. But the force is still going to be the same direction. So the force is going to be upwards. And then, of course, you can again resolve it into a component that's perpendicular, component that's pulling out the conductor. Again, this component that's pulling out the conductor, that is only happening in this idealist case. This is not the ideal way the motor would be constructed. In this theoretical case we are considering, in an actual motor, that component would disappear. They wouldn't be, or it will be very minimal, that it won't actually pull on the conductor that much. Right? So in this exaggerated case, it pulls on the conductor. But in reality, as we'll see in a couple of minutes, it won't happen though. So for now, it's there though. So now the force is going to pull it in this direction. It's going to start to decelerate the rotational aspect of this motor, the rotor that we have. And once, let's say it's completed half a turn, what is going to be the torque on the system? So is this torque direction correct here? The conductor on the left going to experience a force pulling it upwards, right? Conductor on the right now is going to experience a force pulling it downwards because the current, again, starting from the red, it goes positive and comes out, right? So the conductor on the left is getting pulled up, conductor on the right is getting pulled down. So what is basically going to happen is we have created a pendulum in this case. So we start off with this scenario where the conductor is in this orientation, then it flips 180 degree and then comes back, flips 180, comes back, flips 180 degree, comes back. Right? It doesn't do a full rotation. So that is the first problem in this network. Let's say by some mechanism we are able to make this complete a full rotation. Right? Let's say somehow we are able to swap the poles or something which is not practical, but let's say we are able to do it. What is the other problem with the setup that we have? Can we make it into a motor here?
There's one position in which it produces no torque.
Okay, that is one problem. Is there any other problem? So previously I said that I've connected this to a power supply, right? So that's how the current is coming into this power. So the power supply is something stationary on the outside world. And you have these two wires which are going into a rotational mechanism. So basically you're going to, if this rotor continues to keep rotating, you're going to get a twisted pair wire, right? And we do this in the lab where if you want to create a whole long twisted pair wire, we ask one student to hold two wires on the one side and then we connect both the wires to a drilling machine and just turn it on and it will twist it real fast for us, right? So that we have essentially created a very expensive mechanism to create a twisted pair wire. So how do we solve it? Any ideas? Okay.
We make the battery like rotate somehow, or whatever the power source is, like they would have to rotate as well.
Fantastic. So let's say we put the battery on another motor and try and spin that motor. That motor would have still the same problem, right? How do you rotate the rotor of that motor? How do you energize that rotor? Okay.
You use a slip ring or brushes.
Okay, so we use a slip ring or a commutator. So there are differences between so this is what would happen in a previous case where if we excite with a positive negative voltage, it basically goes back and forth, back and forth. And then at steady state, where will it settle down? Will this keep on going back and forth, or will this settle down at some point? Friction would eat away at it, right? So at some point, it's just going to settle down at this middle point where it's the stable operating point. So if you have a bowl and the ball, if you start off at some point in the bowl, it just comes and settle down at the bottom of the bowl, right? So same thing happens here. So what we use to avoid this mechanism of this wire twisting, and at the same time, so we don't want it to behave like a pendulum, we want it to behave like a motor. So what we need to do is, going back to our case here, right? So what we need to do is, when this whatever conductor is on the left, that always needs to experience a force that's pulling it downwards, right? And whatever conductor is on the right must always experience a force pulling it upwards. In our previous case, that wasn't what was happening. When the positive conductor is on the left, it was experiencing a force pulling it downwards. And then when the positive conductor went to the other side, it was still experiencing a force pulling it downwards on the other side though, right? So because of the current direction being in the positive conductor. But what we need to do is flip the current direction. So when the conductor is on the left side, so it doesn't matter which conductor is on the left, whether the conductor marked with the red color or the conductor marked with the black color is on the left, or conductor is on the right. Whichever conductor is on the left, it should experience a force downwards. Whichever conductor is on the right side of the motor should experience a force pulling it upwards. Right? So what we need to do is, then we can't flip the direction of the poles because it's a mechanically attached thing. It's attached to the shell of the motor, so we can't flip the magnetic field around, which is what we'll essentially do in an AC motor by using currents, electromagnets to flip the direction. But in a DC motor, that's not what's happening. Since we have fixed magnet, that's not possible. So what we can do is instead flip the direction of the current that's going into this winding. So that is possible now, right? We have power electronics. We can always flip the direction in which current is going. When we can sense somehow where the conductor is. If its conductor is on the left, then pass current in one direction. If the conductor changes, then reverse the voltage and you can pass current too. But people had created ingenious apparatus to make the system run even before power electronics existed. So even if you have power electronics, there is another problem that's not solved, which is that the wire will get twisted eventually as it keeps rotating. So this thing called commutator, so this is a commutator. This addresses two problems. So this commutator that we have, so this is a commutator, this section that we have. Right, so the way this works is, this is a mechanical contraption, a copper ring. So that thing that you see here, this one is copper. It's a copper ring that is basically attached, soldered on to this wire that we have here. Right, so the rotor wires are attached to this copper ring. And then the way it makes electrical contact with the outside world is through these things called brushes. Right, so these brushes are just graphite blocks. So as these rotors rotates, as the rotor rotates, these graphite blocks are going to make electrical contact, but give mechanical isolation for the system. Right? So that's the black thing that I've drawn here. So these are graphite brushes. For low power motors, these are graphite. Graphite is a decent conductor of electricity, nowhere as good as copper. But for very high power, but the graphite does drop about like 1 to 2.5 volts in the rate, depending on the length of the graphite that you use. But the problem with dropping that much voltage is, let's say you put these DC motors, typically in the past it used to be used in trains and stuff, where each of these motors could carry about 100 to 200 amperes. So you drop 2 volts and you have 200 amperes, that's about 400 volts you're dropping in the motor, while the voltage itself would be typically around 480 volts or something on the DC bus. Right? So that is not a feasible solution. So in those cases, they would instead use a copper itself as a brush mechanism. There are a bit of pros and cons for both of them. If you use copper, it does survive longer compared to graphite, because graphite does to fade away, right? I'll pass this around and you can try rubbing it on your hands and you will see it starts to wear out over time. And when you use graphite, typically you would have to replace these graphite brushes every 6 months or so in a DC motor, which is a very big problem. So when you have to replace this, your production line comes down if you're using DC motor in your industry, and then you'll have to change this, you'll have to clean out the copper ring. So if you look at these copper rings, when I pass it around, you can see that there's a layer of graphite residue. And when this becomes thick enough, it can connect 2 different copper rings together, effectively shorting the rotor windings. So there are a whole bunch of problems that occurs with these copper rings, graphite brushes. So you can instead use copper. But the problem is when you have two metals, one is copper, the other is copper, when they rub past each other, it can cause a lot of scratches on the commutator, right? It makes the operation, starts to wear. So the copper brush might not wear out, but the commutator itself will start to wear out. You'll have fittings on these, which can then start to arc. You'll see a lot of arcing and so on and so forth, right? So we are going to pass positive current through this positive conductor that I marked here in red, and then the negative conductor is the return, and then we connect a power supply outside. If you look at this, now we have mechanical isolation, right? So the current can go through this conductor without the external world getting twisted around. And if you look at what happens to the current on the conductor on the left, keep an eye when it goes to the other direction. So fixate your eye on this copper ring. Once this black part comes here and this copper ring makes contact with the negative, you'll see the current reverses to the other direction, right? So in the left half, if you see whichever conductor, doesn't matter if it's the black conductor or the red conductor that's on the left half. If it's on the left half, the current will always be inside. And if it's on the right half, the current will always be outside. That means we always have whichever conductor is on the left is going to experience a force upwards, whichever conductor is on the right is going to experience a force upward. So we have created a mechanism which can continuously rotate, right? Everybody clear? Anybody have any questions? So let's now look at what the torque profile of the system is going to be. So we have this commutator, I've just shown it in 3 different locations, right? So in this case, the torque was its maximum, which we said was A loop area times I times B. At 45 degree, that is going to be loop area times I times B times 1 by root 2, right? Cos of 45 degree. And in this case, where it's close to 90 degree, tau goes to 0. So the way the torque equation, we can write it down is A times I times B times cos of alpha, where alpha is the angle of this plane. So if I have this plane, this conductor loop, what angle it makes with this along the direction of the magnetic field. So in this case, it's 45 degree. In this case, it's almost 90 degree. Okay. If I plot this for different angles, what is the torque going to look like? Thomas.
Is the non-conductive part on the commutator bigger than the brush?
That's a very good question. Let's say if it is not bigger. Let's say if it's bigger, what is the problem? It is bigger. There is a problem with it being bigger. What will be the problem if it's bigger?
There will be a moment in time when the coil isn't energized.
There will be a moment. No, it's always going to be energized because we do have voltage on the outside. There is going to be a moment where both the conductors are going to be shorted.
Right.
Right. So when, let's say the conductor,
if the brush is too big or the commutator is too big?
The brush is too big.
Oh, okay. If the brush is too big, then it shorts.
Yeah. So there's going to be a period where this brush is going to, so at this angle, right? Exactly here. So this brush is going to short both the top copper and the bottom copper. Right? That's going to mean whatever EMF is developed across this loop is going to get shorted. We are shorting the rotor winding. How can we get around it? We just need to make sure that when we short the EMF in the loop that's being generated is very close to 0. All right, if the EMF in the loop of the coil that we have there is very close to 0, then shorting it is okay because you can short a 0 voltage, nothing is going to happen. If the voltage gets too large and you try to short it, that becomes a problem. So the point at which we short must be such that when the winding is at 90 degree, which is when the commutator segments get shorted, we need to mathematically ensure that the EMF across the loop will be very close to 0. All right. Mathematically, we'll prove that it is 0 at 90 degree, but we need to somehow ensure that too. Okay. Now let's look at the other case where if the brush is small, then the commutator. What's going to happen? Is there going to be a problem if the brush is too small? Well, the opposite is going to happen, right? There is going to be a portion of time when the top conductor and the bottom conductor does not make contact with the external world. Is there a problem? So when I take a coil and put it on an iron core, what have I created? A solenoid and inductor, right? So previously, when the contact was established to the outside world, there was current through the solenoid. Now, suddenly, when the contact is broken, I'm breaking a current in the solenoid. What is going to happen if I try to break a current in a solenoid? Yep.
You'll get inductive kickback.
Yep. So you'll get LdI by dt, which is what we saw, right? Arcing when we try to open a switch gear in a power system. You get this huge arcing when we had a mechanical switch with an RL load in our fifth lecture, we saw that the switch would break down or the power supply or something would get damaged because we are trying to interrupt an inductor current. So we cannot make a brush smaller than the segment where the two commutators are isolated. So this black thing that you see there, that is typically mica material. So the orange things are the copper segments. And in between the two copper segments are isolated using mica, which is a very good insulator. But if your brush is much smaller than the thickness of the mica, right, then there is going to be a time when the top copper ring and bottom copper ring are not going to make any contact with the external world. You're breaking the current that's flowing through the winding of the rotor, which would then cause a huge arcing, which would then burn away the brush or create some arcing or burn away the winding. All right, so the first one is a problem we can fix. If you short two copper rings, well, we just need to make sure the voltage in that loop during that time is 0, which we can work out. But breaking the current in a conductor, that is not a solvable problem, right? And again, you can't put a diode or a rectifier, none of those things here, there, right? Yep.
What do you do if the rotor stops at that position where the windings are shorted?
Rotor stops in this position. Nothing would happen though. We will see how the current, when the winding is shorted. So in this case, we are looking at just one single conductor. So one single conductor will become a problem, right? So once, if you have just a single loop, you have to physically turn it around so that it starts rotating. But in a typical motor, you won't have one single conductor, you will distribute the windings around. So there will always be a bunch of conductors which will have some torque being produced, right? Any other questions? Okay. So this torque profile, the way I've written it, it would appear as if it's going to look sinusoidal, right? Or cosine, phase shifted by 90 degrees, where this is the alpha angle. So is that correct though? This would be problematic, right? If I have a rotational element and if I create a torque that's sinusoidally varying, the net torque is going to be 0. Average of a sinusoid is 0. There is no net torque acting on the system. So basically, I'm rotating this rotor like this, rotating it back. It's like a spin cycle of a washing machine, right? It's not going to effectively keep on continuously rotating the rotor. Then what have I gotten wrong in this picture? There's something wrong in my equation. Yep, James.
Never goes below 0.
Why? Why does it not? That's a very good answer. How do we prevent it from going below 0?
When you swap it, it's another like upper part of the sinusoid.
Perfect. So basically you have an absolute function. And what is really happening in a motor? So the way the torque would look like is like this. And the reason this is happening is the first case would have been true if I didn't have a commutator. Right? If the current is just going in one direction, then the torque would always be this kind of cyclic manner, where if the current is, if the conductor is in the bottom, if it started from the bottom half, it will always swing in the bottom half. If it started in the top half, it will always swing in the top half. But the moment I put a commutator, my current is not going to be just a pure DC like this, right? My current actually flips. So current is initially like this. When the commutator segment changes, the current flips around inside the rotor. So during this portion, I assume the current is always positive in the positive conductor. But if we go back and look at this diagram, on the positive conductor, keep an eye on the conductor on the left that's coming down now. One half of the time, the current is positive. The next half of the time, current flips around and comes out. Right? So the current is like a step function. External, outside the DC current is always going into the motor. But inside the rotor, the current flips from positive to negative every half cycle. So this current is not just a constant value inside the rotor. Outside, it's just IDC, some DC current. But inside, it's positive in half the time, negative in the rest half of the time. So it keeps flipping. So this goes positive, negative, positive, negative. That means whenever this angle goes to the other side, becomes greater than 90 degree and cos alpha goes negative, this would flip around. The current would flip around so that the torque is still positive, right? Maybe any questions? So this is how the torque profile is going to look like. Okay. So what is going to be the so this is the equation that we have already written. So this n term, so here in the diagram, just to keep it simple, we are looking at just one conductor loop. But typically what you'll have is, you will have like n number of conductors in every single slot. So you have a single wire, you can do that n number of times, right? So we are not talking about distributing this yet. It is just the same single wire on the same plane. I have wound it like this. I can again wind it multiple times. So I can put 10, 20, 30, 40 turns, right? So that is what my n term is. N is number of turns. For that single loop that I've shown there, a single loop can have a number of turns. That means the torque, so each of those turns is going to create some torque given by 2RL times I times cos of I times B times cos of theta. And then when you have n of those, it gets amplified by a factor of n, right? So what are going to be the problems with the setup? One problem Ben had identified, where if it starts right at the middle, it's not going to rotate. We need to change the position. What is the other problem? With the torque profile that I've shown here. You all did Fourier series, right? In your 5th lecture. What is this kind of waveform going to have? A lot of harmonics, right? You can resolve it into a DC component, and then you can resolve it into AC component. The problem with those AC component is they are not going to provide a continuous torque. We just saw what happens with an AC component. It starts to create the motor operate like a pendulum, right? So it's going to create oscillations on the rotor structure when you have AC components. So we don't want to have this much oscillation in our torque, right? Thomas, you have a question?
I'm just going to ask, so it's absolute value of cosine alpha? Like you wouldn't say absolute value of I. Is I is constant?
Yeah. If you're looking at, so if this I, let's say it's the DC current coming from the power supply, then yeah, you would put cos of alpha on this symbol there, right? So the equation, the I that I've kept there is the current in the conductor. The way I originally written the equation, the I is not the current coming from the power supply, it's the current in the conductor, which should flip back and forth, depending on which location the conductor is in. But if you want to replace it with the current going from the power supply, then put the absolute for the cos theta function. Okay, so with this kind of profile, the problem is it's going to create a lot of oscillation in your rotor. So when you have a motor which has this kind of torque, you will have a constant speed going, on which there is going to be another component which is riding, which is basically oscillating speed. So ideally you want your motor to rotate at a constant speed, but because of this harmonic content, it's going to have the oscillation on top of it, right? This is going to be quite a bit of a problem. How do we fix it? So if we had instead a 4 set of conductors, right? So 2 loops, such that one loop and the other loop are 90 degrees to one another. That means whatever the torque the first loop is creating would look like this, right? So this is the torque of the first loop, PL1. Again, it should be 90 degree phase shifted to the torque component, but and then what will be the torque profile of the second loop? Would it look exactly the same?
Phase shifted by 90.
Perfect. It's going to be phase shifted by an angle of pi by 2. So this is going to be our torque profile due to the second loop that we have there. Right. So with this torque profile, let's say as this rotor rotates, are both the set of conductors going to keep producing torque at all times for the structure that I've shown there? No. Right? Because if I look at this current position that I've shown, at this point, only the first loop is making electrical contact with the outside world. So current goes into the first loop, comes out of the second loop, and comes out through this brush. The second set of loop is not acting at all. Only the first loop is acting. So during the first portion, so let's say this is the torque of the first loop. Let me draw it correctly so that it's proper orientation. So this is the torque of the first loop. This is the torque of the second loop. During the first half, only this portion, the first conductor alone, tau L1, is the only one that's producing torque. Right? Once this conductor makes full 90 degree rotation complete, it's going to go on to the second set of conductors that we have there. Right? And then current is going to go into the second conductor, and the first conductor is going to be disconnected from the power supply. It's not going to have any current. So the torque is now only going to be produced by the second set of conductor. So we then jump on to the torque produced by the second set of conductor. And then again back, it will be this set of conductor, first set of conductor again, and then second set of conductor. So we'll be riding the top wave of the torque alone without ever going to the lower part, right? So everybody clear on this? How the torque,
Does it not like create any arcing when one of the windings?
So that's one first problem that we'll have in the system. There are two problems with this current apparatus. So there is going to be arcing. We'll take a look at what these other one is. Any other questions? Everybody understand how this operates? Okay. So this is similar to what you would get with the diode bridge rectifier, right? When you have a diode bridge rectifier with an AC power supply, you basically ride the top half couple alone, right? What will be this point? Let's say this value is tau max. What will be this minima of the torque profile? So our actual torque that's being created would look like this. So let's say this is tau max, which is 1 Newton meter. What would this value be?
0.6. 6, 7 times the mass?
Oh.
I don't know.
What angle does sine and cos and sine interact? 45 degree, right? That's where it's 1 by root 2. So that's just going to be 1 by root 2 of 1 Newton meter, all right? And then once we have this wave, we can take average value of it, right? Figure out what the average value of it is going to be. And that is going to give you your average torque, which comes out to about 0.9 Newton meter. Now, this still has a little bit of oscillation on top of it, which is not very optimal. How can we further reduce it? Can we reduce it, or is this the best we can do with our motor?
More conductors.
More conductor, perfect. So we just put more conductors which are displaced, right? We have, in this case, we have 12 slots in this rotor, right? Previously, we had 4 slots. Here we have 6 set of conductor loops. So we have a whole bunch of conductors which are phase shifted by 30 degree, 30 degree, 30 degree, and so on and so forth. So you create a whole bunch of loops like this. Just a second, Ben. So we have 6 set of coils here, and this is the torque profile that we get for each of those coils. And the output torque is not going to go all the way down to 0 for each coil, because once this point hits, it's going to jump to the other coil, which is now executing the maximum amount of torque. So we're just again riding just the top half at alone, right? So with that profile, we have this waveform, and the average comes out to be very close to DC, right? We have eliminated torque pulsation. We still haven't eliminated the problem Jonah mentioned, where we are interrupting current in each coil, right? So that is still a problem that we have to solve. There's another problem that needs to be addressed. Anybody has an answer for that? While you keep thinking about it, then.
Is the angle of the windings, is that also to decrease torque ripples, or is that for some reason on the rotor?
Oh, the reason we have slewed it like this. That is so when we have, let's say this rotor is not slewed, right? So here we have air gap and here we have iron. As this rotor rotates, the magnetic field will try to prefer to go through the iron, but not through the air gap. So as the rotor rotates, the magnetic field keeps moving around back and forth, right? So that is going to create some kind of pulsation in your rotor torque. So you kind of slew it so that when the magnetic field from here goes from this point to this point, the magnetic field on the bottom would come from this point to this point. So on an average, you don't get that pulsation. There is another thing which also something called cogging torque. When the rotor iron is aligned with the magnet, that is where the least reluctance is, and the rotor would like to stay at that point. So when you start a motor with very low current, the rotor won't rotate at all because it likes to stay at that point where the iron is very close to the magnet. But the problem is then you would have to put some amount of current for the rotor to start rotating to avoid that you slew it, so that on an average, no point is closer to the iron than any other point, right? So that skewing is a little bit more complicated topic. We'll address it, but that's the idea, the 2 reasons why we do it, right? Anybody else any other questions? Okay. Can somebody tell me what are the problem we have with this set of coil that we have? Copper is not cheap, right? So we put 6 set of coils, and we are only utilizing at any given time 1/6 of the coil. In this case here, we had 12 set of coils here, right? At any given time, we are just using 1/12 of the coil, which is total waste of copper that we have. And the other bigger problem is if you look at the average torque, going from 2 set of coil to 6 set of coil, it didn't increase that much, right? If you put more number of coils, you would expect, if you put 3 times more number of coil, you would expect your torque to be 3 times as larger, right? Otherwise, it wouldn't make sense economically to create a motor with so much copper being utilized. So this is the first problem that we have. The second problem, the first problem was what Jonah mentioned. Every time we interrupt the current, or every time the coil changes from one set of coil to the other one, we are interrupting the current, which is going to be a disaster. So this is not how we'll wind an actual motor. So in an actual motor, what we'll do is we'll take one winding. So whatever coil we had here, this one coil will go and complete this. And then the same wire would make a series contact with the other coil and come back. And then this coil will then connect back to the first coil, so that there is always current flowing. Even if the second set of wire are not making contact with the external world, it is going to carry the current from the first set of coil that is making contact with the external world, right? And as it rotates, then the second set of coil will now carry the current and then transfer it to the first set of coil too. So at any given time, all the coils are carrying current and all the coils are producing torque, right? Okay, so let's now look at what the torque profile, structure of the motor is going to be. Before I jump ahead, let us see what the EMF is going to look like. Can somebody tell me? So we had our magnets going north, south. I usually don't like to use slides, but as you can see, my drawing is awful. That's why I had to create a presentation. So let's say this is what our winding looks like. And we have B field parallel to the winding in this case. And then the second scenario is again, we have north, we have south. And then we are going to look at the case where the winding is at 90 degree. Right? So this is alpha 90 degree and this is alpha 0. So let's take a quick, just make a guess. In which of these two cases, if I measure a voltage across this, is the first case going to create the maximum EMF or the second case going to create the maximum EMF? So how many of you say it's the first case? Just raise your hands. Just take a guess. How many of you think it's the second one? Right? Somewhat intuitively, it kind of feels it would be the second one, right? But again, that's where intuition always gets us into trouble. Can somebody tell me what equation would I use to figure out what the EMF is?
The change in flux over time.
Perfect. So we have this expression E equal to N d phi by dt. So E equal to N d phi by dt. What is our flux going to be? Like, let's start off with the second case. What is our flux going to be in the second case? So the length of this coil is L. The total diameter of this coil is 2R. What is our flux going to be? How do we calculate flux? Go back to this equation, right? Is the B field changing? It's from a magnet, right? So the second case, that's going to be B. If the B field is not changing, then what can we do? What does that integral resolve to? Anybody? What was it?
B times area.
B times the area. Thank you. So the area is just 2RL. Okay? So the B times the cross-sectional area. What is going to be the flux in the first case? Is there a flux through the coil in the first case? No, right? Flux is only the component of field that is perpendicular to the surface area. That's what this B dot ds term means. So when you have some surface area and you have some B field, right? The vector for the surface area would be the component perpendicular to the surface area. So the dot product is whatever component is along the perpendicular component to the surface area. Right? So whatever is tangential to the surface area, that does not create any EMF at all. So the first case, so this is case 2. In the case 1, flux is going to be equal to 0. Right? Because integral B dot ds, there is B. B doesn't go to 0. D is from the external magnet. But this dot product, that makes this term 0. Right? Because there is no component of flux that is going through the surface. It is all going tangential to the surface. So that's not going to create any flux at all. Okay. What is it going to be for any angle in between?
BA cosine theta.
What was that?
BA cosine theta.
All right. So BA cosine theta. So it's going to be, so what flux is going to be for any angle alpha or theta. What did I use this one? Alpha. So we have B 2RL area times also alpha. Is that correct? Let's do a sanity check. If alpha is equal to 0, our flux has to be 0. Right? But in our case, that is not what's happening. So it should be sine of alpha. So from torque, in the case of torque, when the angle was 0, the torque was maximum. But in case of flux, that's not the case. When the angle is 0, the torque flux is equal to 0. Okay, so once we have flux, we can just go back and substitute into our EMF equation, which is equal to N d phi by dt, which is then going to be equal to N times B RL 2 times differential of sine alpha. That is going to give us cos alpha. This term, if you look at it, it was exactly the same as what we had for a torque. So a torque was again N times 2 NBRL, which was the area times cos of, sorry, times current times cos of alpha. So this term is exactly the same as this term. I am missing a term here when I did the differential. Anybody want to tell me what term did I miss? Is the differential of cos alpha, sin alpha with respect to time just cos alpha? No, differential of sine. If I had sine of t and I did d by dt, that would give me cos of t. Right? But I'm not doing differential with respect to time, I'm doing differential with respect to some other variable alpha. So I need to do d alpha by dt. Okay, so this would be our rotational speed omega, because this is the rate at which the angle is changing, and that by definition is omega. So this is 2 times NBRL omega times cos of alpha. So if you look at the expression for the torque, so let's call this some constant K, Ke, and let's call this some constant Ke, back EMF constant. So our torque is going to be Kt times the current times cos of alpha for that one winding, one loop. And our EMF for one loop again is going to be equal to Ke times omega times cos of alpha. So this is called the back EMF constant. And this is the torque constant. But from our expression, Ke and Kt look exactly the same. So Ke is always going to be equal to Kt. There is a caveat though, assuming that both are in the same unit system. So if Kt is in SI and Ke is in SI, or if this is in imperial system, this also needs to be imperial, so on and so forth. Typically, when you look at a data sheet, that's where things get confusing, because at least in US, they would give this in pounds per meter or something like that, and this they would give it in voltage. So whatever we have, right, volt second, while this would not be in Newton meter per ampere. So this would be in a different unit system, this would be in a different unit system. So when you look at an online data sheet and you see Ke different from Kt, it just means that they have used different units for both of them, right? But when you have both of them in SI units, so if you had this as, so this, yeah, this would be volt second per radian, and then this would be Newton meter per ampere. Both of these, if you resolve it into, the fundamentals of SI unit, they would have to end up being the same, which it would. Okay, so in our course, we'll always use SI units. So this Ke is always going to be equal to Kv. So let's go back to our first question. Can somebody now tell me which of the two configurations would have the maximum EMF? Is it when in case 2, is it EMF maximum or case 1? Yep.
Is it rotating?
Was it?
Is it rotating?
Yep, it is rotating. Yeah, if it's not rotating, then EMF is 0, right? The flux has to change, right? So this is a case where it's rotating and it ends up being in this position at this point in time. So which of the two would have the maximum EMF? Case 1. So here is where EMF would be max. Right? Again, it's very counterintuitive because you would somewhat think, hey, if the flux is maximum, that's when the EMF would be maximum, but that's not the relationship between EMF and flux. Right? It's the differential of flux. If the flux is maximum, it doesn't matter. It is whether the flux is changing or not. Right? So that is what really matters. So you could have, you could be traveling at 100 miles per hour, but if your velocity is not changing, there's going to be no force on you, there's going to be no acceleration on you. So the magnitude of the flux itself doesn't matter, the rate at which it changes is what matters. So somewhat luckily for us, through mere good luck, through all these nice equations we have, it ends up being that the EMF is 0 when the windings are at 90 degrees. So going back to the question, of what would happen when the brushes are bigger than the commutator segment that Thomas had asked, we will end up shorting the winding for a short period of time. But the shorting happens when the conductor is at 90 degrees. Right? At that point, the EMF is very close to 0. It won't be exactly 0 because the B field we are looking at looks like this in our ideal case, but in reality, it will get twisted around so that even at that location, there will be a tiny amount of EMF, which we'll take a look at, called the armature reaction. But for an ideal case, at least the EMF is 0, so we can safely short the two winding externally. So the copper segment, the brush can be a little bit bigger than the copper segment. right? Anybody have any questions? Okay, so let's go back to our lines. So this was the two magnets that I drew, right? So the one on the left is, let's say, North Pole, the one on the right is South Pole, right? And then again, the face side is what I marked as North and the face side is what I marked as South. So back side would be South for this, if it's North on the face, and then if it's South on the face, the back would be North, and then the field lines close to the shell of the motor itself, okay? And then our wires come into, our external wires, right? They come into this mechanical, this copper segment here, and I have this brush right here. So this is just a pure graphite rod, and there is a spring attached to it, and it comes through this slot that I have here on the top, and it goes inside and makes contact with the commutator segment that I have on the rotor, right? As the rotor rotates, so this is the commutator segment that you see here. It's much better. So the copper rings, the brush is just gonna make contact with the commutator segment as this rotor keeps rotating, right? So these are the commutator, and as you can see, this is put on a brush. So what happens is on a spring, so over time this brush starts to wear out. So the spring will keep on pushing it so that even if the brush wears out, it can still make contact. But it's only up to some point, right? If it wears out too much, then there is no amount of spring that can push, that can make continuous contact. It's going to get to some point where it gets to a very small length, you'll have to replace it. And for typical DC motors in industries like train locomotives, still some old trains still use them. They would have to replace this every 3 to 6 months. Okay. Even in our labs, what we do is we would have to replace sometime. When you do some experiments, you'll see that as you rotate the rotor by hand, the resistance that you previously measured is not the same resistance, right? Because as it rotates, sometimes it makes good contact, sometimes it doesn't make good contact. For lab applications, it's fine. And usually when it gets too worn out, we just throw the motor and get a new motor instead of replacing the brush because it's pretty cheap. But typically in an industry, you would have to keep on replacing them. So this one that we have here, right? Where the text is shown. Okay. So this is the commutator segment. As you can see, those are all copper. And the thin line that you see in between them, those are the mica segments that are insulating the two copper commutators. All right, in a DC motor, the number of brushes that you have would be equal to the number of poles. In our case, we're only going to consider a case of 2-pole DC motor. With higher power motors, you would have higher number of poles. But nowadays, DC motor are more or less for low power applications and stuff. That too being significantly phased out by BLDCs. So we won't consider anything other than a 2-pole motor for this class, but we will consider higher pole when we go to AC motors, which are typically more than 2 poles, right? So, and then what we have here, we have the rotor structure. So the way the rotors are made, it is not a single iron that's being chopped and cut into, right? We have these thin plates. I'll show another diagram for that. We have these thin plates that are stacked together. So you can't see that very clearly here, but I can pass it around and you'll see that these are all actually thin plates of iron that are stacked up together, each iron insulated from one another, laminated from one another, so that they don't electrically conduct. And then what we do is we start off with, say, a first winding. I take a first wire, put it in this one slot, take it 180-degree back, which is called a full pitch. You can go even like a little bit lower angle too, which we'll again consider later. But for now, we're going to assume we start in slot 1. We go all the way back, close one winding, bring it down, and do this n number of times. That was the n that I wrote there in our equation for one loop. Once I've done it 10 times, I take the same wire, right, and I connect it to the commutator segment that I have here so that current can come from the external world. And then the same wire, without breaking contact, I go to the next slot and do this n times. And then make contact with the commutator. And then the same thing I take, make n turns, make contact with the commutator, next commutator, so on and so forth. So as the rotor rotates, there is always one set of conductors that is making contact with the external world. And since all of these conductors are in series, the current flowing in that loop will also be the same current flowing in all the other loops, right? So I can create multiples of the torque, not just torque from one conductor loop alone, right? And then this whole rotor structure, we put some bearing, right? And this whole thing goes inside this motor. The commutator going this way, right? and then we put some faceplate, cover both sides, and that's about it. So typically with high power motors, you would have bearing on both sides because the motor is bigger. But in this case, the motor is thin, is not heavy enough. So there's just bearing on one side. So this bearing is very critical because because the rotor can't float in air. There is no levitation mechanism, right? If you leave it to it, the rotor will go and attach to one of the two magnets because it's an iron structure. So the way you have the tiny air gap, you can't even see the air gap visually, right? It's just 1.5 mm air gap length that we have there. So visually, it's not even perceptible. So the manufacturing tolerance are very, very tight on these. So you will have a faceplate on which this bearing rests so that the rotor can rotate and still have mechanical support to keep it kind of, I shouldn't use the word levitated, but levitated in the air, all right? Do you have any questions on the structure? Okay, I'm going to pass this around. You can take a look at it. Be careful when you pull the rotor out. There's quite a bit of force to pull it out. Don't get your fingers jammed in there. Okay, so let's go back to our presentation. So this is the plate that the iron rotor that we have. So these are made of these thin plates, and these plates are all stacked up together to create our rotor stack that you have. All right, can anybody tell me why we are using the thin plates instead of taking a block of iron and just cutting slots in through it?
Reduce eddy currents.
Perfect, reduce eddy currents. So let's say we had this rotor structure, right? Let's say I'm looking at this rotor structure from the front. Just to simplify, let's assume the diameter is also L and this length is also L. Right? What would happen is as this rotor rotates, when it goes from the north pole to the south pole, the magnetic field across the rotor's face is changing. Right? We only looked at what happens to the EMF being induced in the conductor because that is what is desirable for us. But when you have iron, EMF can be induced across the face of the iron as well. Because you have this electrically conductive material that's rotating. Even if it's not electrically conductive, you'll have EMF induced. But if you have electrically conductive material, the current can then start to flow. So as the rotor structure that we have, as it rotates, this, let's say we are looking at this face side, as it goes from the north pole to the south pole, the flux is changing on that face. So when you have a changing flux, E equal to d phi by dt, right? And that in turn is going to be dV by dt. The area of this loop is not changing. So let's just call it L squared. Or if you want to have the R term, let's ignore the R term just for simplicity. So the area of this loop is going to be L squared. All right, so we have fluxes B times the cross-sectional area. The area is not changing, but the flux is changing. B is changing, so I can't pull that out. So this is going to be the EMF that's being generated across this face of this iron. And this in turn is going to carry some current through it. So let's say the resistance of this side, let's say here, this is the biggest loop that's created. Let's say this resistance is R. And then the resistance here is also, on this side is also R, and R. So we have effectively current is going to be equal to, or we can directly compute the power. Power lost in this face of this iron core is going to be E squared divided by total resistance, which is going to be 4R. Right? So that will be L power 4 divided by 4R times dV by dt, the whole square. Now, let's say instead I'm going to stack it up into these plates. Instead of putting a solid block, then I have these plate, this plate. At first, it will appear as if, yeah, the surface area is going to be the same in both cases. The flux is going to be the same. But somehow the EMF induced across this and the current, the power lost to the structure is going to be much, much lower. Okay. So this length is still L. This total length, if I take all these tiny segments, so let's say there are N plates. So the total length of all these stacked N plates is going to be L. So each of those plates have a length of L by N. Right? So the resistance again for going from this side to this side is R. So there's going to be an EMF induced across this plate like this. But now these EMF loops are tiny, right? Because there's insulation material between the top plate and the bottom plate. So the EMF current cannot jump through those plates. So it is confined just to the tiny plates around. So what is the total resistance of each of those plates? That is going to be equal to 2R plus this total length. If it had the full length, it would have been R, but only a portion of that length is there. So R times L divided by N. So R divided by N, sorry. Right? It had the full length in the previous case. Across this full length, the resistance was R. right? So for length L, the resistance was R. For a length L by N, the resistance would have been R by N, right? So this is the resistance that we have, and each of those generally have a EMF induced across them, which is going to be equal to, again, d phi by dt. But in this case, the phi is a bit different. So we have dV by dt. Phi is going to be area again, R times, not L though, but L by N, because area of each of these loops is just R times the tiny height of the plate that we have. All right, so this is going to be our EMF, and then we can take E square divided by R again, which is going to be equal to L square. So this resistance is R, length is L. Right? So we have the area would have been L times L by N for each of those plate, area of a plate. Right? So we have L square divided by N. So our E square would be dV by dt square times L square would have been L power 4 divided by N square divided by the resistance. This R times 1 by N would be very small because we are having N number of plates. If the 10 is being extremely large, as you'll see in the motors that we have, we probably have like hundreds of plates stacked up together. This term can be negligibly ignored, right? So the resistance is effectively just 2R, right? So this is the energy lost in one plate, but we have N plates though. So the total energy lost in N plates would be, in the second case, would be dV, power lost in the second case would be dV by dt whole square. We have that same L square term here as well, right? Divided by 2 times R instead of 4R. But we have the advantage of 1 by N square. And then that was for one plate. So for N plates, it will be N on the numerator. So this N square gets cancelled. We are still left with a power that is 1 by 2N, smaller than the power that we had in this case. So it will have been, so the power in a solid block is equal to N by 2 times power of the plates combined. Right? So instead of using a thin plate, if you had a whole block of iron set there, you would use N by 2 times more power than using individual plates and stacking them up together. So this is called eddy current losses. Just to avoid those, you use these stacked plates instead of putting a solid block there. Right? Do you have any questions on how this works? Yeah.
Sorry, could you just clarify exactly what part of the motor this is?
Oh, that's the rotor. So these plates stack up and the rod goes through. So whatever you're looking at, it looks green because of the insulation that you have. When you pass the rotor around, you would have seen the green color structure, right? That's skewed. Okay. So that's the structure that we are talking about. Right? Okay.
Can you go back one slide? Just to clarify, are you saying that little r is the length or like the radius? Okay, because then on the other side you have big R. Is that also the resistance?
Yeah, all R's are resistance.
Okay.
Yeah, big R would be so little r is the resistance. So if the current is tracing this outward path, right? Little r would be the resistance for this first half, and then resistance R, little r here, and then little r here, and then little r here. So total resistance would be the capital R, which is 4R in the first case.
Okay.
In the second case, it will be little r top and bottom, 2R. And then this vertical height is much smaller than the previous case. So the resistance would be little r times 1 by N. Right? The resistance is going to be a factor of N divided. So if you have like a long wire, cut it into 10 parts, the resistance of each part would be 1 by 10 of it. So that's what we're doing there. Right? Any other questions?
On the next slide, where you have like P solid equals 1 over 2 P plates, is P plates the one on the right there?
P plates is the things that we have stacked and compressed together. Right? Whatever the motor you're passing around, that has different individual plates. That is what I've shown in this diagram to where it's stacked up together as individual plates. Each of the plates are laminated, so current can't flow from one plate to the other. The one that I'm showing on the left, that would be the P solid. That is not the structure that we have in the slide, not the hardware that we are passing around. Right? This would be the case where you get a solid iron block and just cut holes through the iron block, but not cut the plates. Right? It's just a solid iron block, so current can flow through the full face of the iron block.
So, okay, so then P plates equals the dB dt squared L squared R, that like formula.
So whatever I wrote here, this is all for solid, right? This is the expression for end plates. This is for total solid. Here, whatever I derived was for purely plates. Any other questions? Thomas.
On the last slide, where does the 1/2 factor come in for solid equals n/2?
Oh, this in the previous case we had 4R, in this case we have 2R.
Oh, okay.
Because here we approximated the R times. Any other questions? Okay. Let me just take 2 more minutes. Again, it's being recorded. Hopefully, it's being recorded. Let me just go through the structure and we'll be done. So we have these plates stacked up together. We have a rotor bar going right through it. And then the way we wind these conductors is, again, this is not the structure that we have, of the rotor I passed around, because that had 12 slots. Here I'm taking for simplicity just 6 slots. And again, there is a skewing in real motors, and ideal case, we don't consider skewing. So we have a conductor starting from here, going here, coming down. And in reality, I would do this n number of times, right? I would do this n number of times. Just to not cloud this image, I'm just creating a single loop alone for this diagram. But whenever you see that loop, think of it as again set of conductors going and coming out. And once I'm done with the 10, so I have this conductor go down, come up, and I've done this n times. The next turn would go to the slot behind it, the same wire, right? We are not using a different wire, right? And then we do this again n times for the 180-degree slot. And then once that's done, you go to the next slot. Do this 180 times. And then once that's done, you come back to this original slot, right? But you can't terminate this wire though, because this is actually going down. This wire came out, this wire is going in, so you can't terminate them because there is no open wire here. So again, what I do is I take this conductor inwards and bring it out of this conductor. And I keep doing this again and again until the starting wire and the ending wire can touch each other, right? In which case I short them and close it out. Right? So I do this again, and we'll end up winding it up. I'll draw a better winding diagram. We'll do a winding diagram in a planar structure. This is just to show what happens in a motor. So whatever wire started, you'll end up with the same wire shorted out in the end, right? And this is what the top would look like. So this is a rotor structure, and then each of those loops that we created would have its contact with the commutator. So that's what you have seen. You have seen a hook to which the wire goes around. So this is where your copper brush, the graphite brush makes contact with the copper commutator segments that we have. And this whole thing, so this is where the contacts are made. Right? And as this rotate, it keeps contact. Again, those who have to leave, that's absolutely fine. Please go ahead. And then the whole thing is supported by these bearings. So bearings are just mechanical apparatus where the rotor is connected to the mechanical, and then the stator is making contact here. And there are a bunch of balls inside. So they'll allow you to rotate, right? With providing mechanical support though. So we put bearings on both sides. Then we have these magnets, right? So this is a north pole. This is a south pole magnet. And this whole magnet is enclosed within this shell that we have. And then this whole thing is closed with 2 face plates on the back and the front, right? And this is the motor that you'll see in the labs that you have. And the commutator brushes are basically going into these 2 slots that we have here, right? I have posted a 3D model of this. You can use AutoCAD to look at it. In AutoCAD online, there's a feature where you can create a plane and then move the plane around to see the windings go around. Those of you who have access to PTC Creo, I have posted the Creo file. With that, we'll meet one by